All right, guys. We were talking the last couple of days about diffraction and interference of light, and we learned two equations that go along with that. First one was lambda is equal to d sine theta over n, and then the second one was lambda is equal to xd over n times L. One of those equations is valid all of the time whenever we're dealing with interference. Which one is valid all of the time? First one or the second one? First one, yeah. And obviously the second one is the one that's valid only some of the time. Now, when I say some of the time, it's most of the time, right? The vast majority of times you can use both equations. What's the rule of thumb that we use to determine whether the second equation is valid or not, Tom?
L is smaller than 10 times x.
Good. So we're going to say if L is bigger than 10 times x, then we can use it. If L is smaller than 10 times x, then we can't use it. Does that make sense? If it's bigger than 10 times x, it's good to go. Okay? It's still an approximation. It's not perfect, but to the correct number of significant digits, you're going to be okay. Okay? But past that, we don't really know past that, but it doesn't really matter past the right number of significant figures. If L is not bigger than 10 times x, then all bets are off in terms of its validity. So we're not going to use it if that's the case. Listen, if we find that it's not valid, we want to use it because let's say we have the value of x, we have the value of d, we have the value of n, we have the value of L, fits perfect into that equation, but we find that L is not greater than 10 times x. We got to use the other equation. How do we go about using the other equation if the variables that we have are the variables that are on the board there right now? How can we use d sine theta over n when we don't have what theta is? We've got to find it, right? We're going to find it. Okay, if you remember what things look like here, back to that original diagram we drew here. Okay, if this is, let's say, a line that goes from the slits to the screen, that would be L. Okay, this would be X. Okay, let's say we're trying to find, we got the distance there from the central maximum to the second maximum. This would be theta. So if we multiply x by 10, and it's not, and it ends up being bigger than L, 10 times x ends up being bigger than L, and we can't use this equation, then let's use a little bit of trigonometry here. Let's say tan theta is equal to x over L. Find theta, and then plug it into this equation to find lambda. Does that make sense? Now, that only works if you're measuring it from the central maximum, right? Okay, it doesn't work if you're going from the third to the fourth order maximum, but you're not going to encounter a problem where you need to use this equation right here when you're dealing with the third and the fourth maximum. Okay, if you got to use this equation, if you have to use this equation, it's going to be, you're going to be given the values as measured from the central maximum as opposed to from the third or the fourth order maximum. Make sense? Here's another little rule of thumb. If you're not dealing with the central maximum, if you're dealing with, let's say, the third and the fourth order maximum, you're just about going to have to use this equation because you have no way of finding theta at that point, right? Okay, you could actually find theta using the law of cosines or the law of sines or something like that, but in the end, this equation still wouldn't work unless it's measured from the central maximum. So if it's not measured from the central maximum, it's good to do this test anyways, but you probably don't have to worry about it because there's no other options really. If it's not measured from the central maximum, you're pretty much going to have to use that equation. Okay? So x is the distance between the maxima or minima or maximum and minima, whatever. L is the distance from the slits to the screen. What does d stand for again? Little d? Right? Good. The distance between the slits or the openings there, distance between the holes. And what else we got there? N. What does N stand for? Don't tell me what it stands for. Just tell me what N is in this case right here when we're going from the central maximum to the second maximum. 2, right? If we're going from the third maximum to the seventh maximum, N would be equal to 4. If we're going from the first minimum to the second maximum, N would be equal to what? 1.5, right? So this is 0.5, this is 2, 2 minus 0.5 gives me a value for N of 1.5. All right, so our questions on 691. Any issues with those questions on 691? 3? Any others? No? Okay, let's take a look at number 3. It says a student used light of wavelength 5 times 10 to the negative 7 meters. Remember what we said when we're solving for a wavelength? We always expect to get a value in that range of 10 to the minus 7 for these kind of questions. Not for all questions, but for diffraction interference questions, we always expect to get 10 to the minus 7 meters because that's visible light. Okay, if we converted that to a frequency, we'd find that it was in that range of 10 to the 14 hertz, visible light. Found that the distance between the third node and the central antinode is 1.00 times 10 to the negative 1 meters. Screen is 1.2 meters away from the slits. How far apart are the slits? It's a good idea, Caitlin, in this case, I think, to draw a diagram of the nodes and antinodes in order to determine what the value of n is. Okay? If it says the third antinode and the fifth antinode, you're probably okay with just subtracting 5 minus 3, right? But if you're dealing with a node and an antinode, right, one's kind of in between, and then one's one of the bright spots, then I think it's a good idea to draw that picture out so that you can count off what n is. So let's say we're just showing one side of it here. Okay, let's say that's our central antinode. Another name is our central bright spot, our central maximum. Okay, this would be our first order maximum, second order bright spot, third order bright spot, fourth order antinode, whatever you want to call them. Okay, we're going from the central antinode right here to the, what is it, the third node? So 1, 2, third node right there. Caitlin, what's n going to be in that case? Good. N's going to be 2.5. Now, we got the variables of everything, the values of everything else here. Lambda is 5.00 times 10 to the minus 7. We've got the distance between the third antinode and the central antinode as 1.00 times 10 to the minus 1. That's x, right? Something's 1.2 meters. What's that? That's right. Yeah, it's L, big L, or little l. Okay, in the equation, it's actually little l. I always write it as big L, so it doesn't look like a 1, right? We're looking for how far apart the slits are. Maria told me a minute ago that little d is the distance between the slits. So we're solving for little d. Now, I think when you look at these givens, you're going to want to use the second equation, right? Lambda is equal to xd over n times L. Now, we're going to do that little check. Okay, we got it here because we're dealing with the central antinode. We could find the angle if we needed to. Okay, now, what a lot of teachers would tell you to do right now is say, okay, find the angle. Make sure it's under 10 degrees. If it's under 10 degrees, then you can use this equation. I think that's a waste of time. Okay, if I tell you to find the angle and it's under 10 degrees, well, if you've already found the angle, why wouldn't you just use the other equation that we know always works? Okay, my little rule of thumb helps us to avoid even finding the angle. That rule of thumb, as Tom said a few minutes ago, was basically if L is greater than 10 times x. Okay, is L greater than 10 times x? Well, L is 1.2 meters. X is 0.1 meters. Let's multiply x by 10. We get 1 meter, right? Is 1.2 meters greater than 1 meter? Yep, barely. So we're dealing with an angle here that's probably 6, 7 degrees, okay, but it's still okay. Okay, it's under the cutoff, and it's clearly under the cutoff, so there's no issue whatsoever, even though it's close here, there's no issue whatsoever with using this equation. Now, if you wanted to find the angle and go back and use the other equation, you could. In fact, when you're dealing with an angle that's as big as this one is, you may even find to the third significant digit that the answers are different. I've seen that before on diploma exams, actually. But if that's the case, they'll key both of them correctly in a numeric response. So you wouldn't have to worry about, if you're under the cutoff, you don't have to worry about, oh, wait, I get a different answer using this equation, using this equation. They'll pretty much be the same, and most times they'll be exactly the same. But if they're slightly off, both answers on a numeric response question would be marked correct. All right, so we're solving for d here. We're allowed to use this equation. Let's take the n and the l up by multiplying, the x down by dividing. So we end up getting 5 times 10 to the minus 7 times n, which was 2.5, times l, 1.2, divided by x, 0.10. Do the math there, and I think I think, Caitlin, we're going to end up with 1.5 times 10 to the minus 5. Caitlin, what was the problem with that one? You counted what, sir? Okay, okay. Anybody else do that? But make n is 3? Yeah, I mean, it's a multiple choice question on a test. You got to figure that you make n 3, that's going to be an option, right? Because, I mean, how easy is it to make that mistake? The central antinode, the third order node, we see the number central, we see the number third, and then we just subtract the two, right? Okay, third order node. Would have been a good idea for us, actually. I didn't do this, but it's probably not a bad idea to draw attention, especially when you're dealing with two different terms there, node and antinode. Draw attention to that. So it reminds you that something is 0.5, right? All right? You still okay about that? Okay, the second set of homework we had was page 693. These involve diffraction gratings. Now, the only thing with diffraction gratings that makes it different than Young's double slit experiment, which was the question that Caitlin asked me about, two openings, right? Young's double slit, two slits, is that these ones have hundreds or even thousands of slits, of openings. Okay, that's not a big deal because it produces essentially the same pattern. The one thing that we have to deal with, though, is that we're typically not given a value of little d. When we're given a value, say, 2,500 lines per centimeter, 1,000 lines per centimeter, how many lines per centimeter? We're not given the value of d or trying to find the value of d. Rather, all of those things represent 1 over d. So how do we get d? 2,500 is 1 over d. Daniel, how do we get the value of little d? How do we get the value of little d, Devin? Yeah, just flip it over, right? D goes up, 2,500 goes down, so D would end up being equal to 1 over 2,500 there. So whatever that equals, it would be in centimeters. Of course, we'd want to convert that to meters, unless you're given the lines per meter instead of lines per centimeter. All right? Once you got D, this question is exactly the same as what we've been doing for the last day and a bit here. All right? Any issues that we have on page 693, 1, 2, or 3? 3? Okay. So go get number 1 and number 3 here. Tom, what is 1 over 2,500, by the way? Four times 10 to the negative 4 centimeters, which I might as well convert that to meters now while I'm at it. That's going to be 4.0 times 10 to the negative 6 meters, right? Because a centimeter is 100th of a meter divided by 100. Okay, you got the value of D. We got third dark node, central antinode. Got another one of those ones, right, Caitlin? Third dark node, central antinode. Let's draw that out again. Again, especially when you're dealing with a node and an antinode, it's probably a good idea to draw it out. This is our central first, second, third, fourth antinode. We're going with the central antinode and the third node. 1, 2, third node. Tom, what's n going to be there? 2.5. Same as it was for that last question, right? 2.5 because we're dealing with the third node instead of antinode. We got a 20 centimeters here, or a 0.20 meters. We also have a 0.50 meters here. What's the 20 centimeters thing here? The distance between the central antinode and the third dark node is 20 centimeters. What variable is that? Is that x? Is that L? Is that, what else we got? D? We already got D, so it's either going to be x or L, right? X, good. This one's going to be L then, right? And we're trying to find lambda. So we want to use the equation lambda is equal to xd over n times L. But we got to check, right? We got to check to make sure that we're allowed to use it. So the check for us, the rule of thumb is if L is greater than 10 times x, then we're good to go. Is L greater than 10 times x? No, it isn't. Wait a second. We can't use that equation. Now, if I recall correctly, it's been a while since I've done this question, basically last year since I've done this question. But if I remember correctly, the answer that they give you in the textbook reflects using this equation. So I think it's this question where they made a mistake and they didn't check to see if they were allowed to use this equation. Okay? I don't care what the answer they put in the textbook is. Okay? I care what the right answer is. We're not allowed to use this equation because L is not greater than 10 times X. Does that make sense? That's rare that that happens to us. Okay? That doesn't happen very often. But you can see that occasionally it does. That means we've got to use lambda is equal to d sine theta over n. We don't know what theta is, though. Well, let's draw it out. Here's L. Here's X. We know what the value of L is, 0.5. We know what the value of X is, 0.2. We want to find the value of theta right here. So we're going to say tan theta is equal to opposite over adjacent, 0.2 over 0.5. Or theta is the inverse tan of 0.2 over 0.5. What's that equal, guys? The inverse tan of 0.4. 21.8 degrees, clearly over our 10-degree threshold, right? So we got that angle. Now the question is not so bad. D 4 times 10 to the minus 6 times sine 21.8 divided by 2.5. You know, if there's ever a question that they throw at you that's kind of a mean question on this concept, this is it. Okay. How easy is it to make a mistake on this one? First of all, they don't give you the value of D. You got to flip it over. And then you got to convert it to meters. Second of all, the value of N, they throw in a node in there instead of just antinodes. So there's a 0.5 mixed in there. Thirdly, you want to use this equation, xd over n times L, but you can't because the angle is 21.8, which is quite a bit bigger than 10 degrees. So we got to find theta and plug it in. I'll tell you what, if this question appeared on a diploma exam, even though we've gone through it here, and it doesn't seem all that crazy once we go through it, the success rate of this question provincially would be 25%, maybe 25%. Okay. You guys are going to be in that group of 25% that gets it, okay? Not the 75% that doesn't get this question. What does that work out to be, by the way, guys? I'm going to say something times 10 to the minus 7 because it's visible light, right? That's my prediction that it's 10 to the minus 7. .04 times 10 to the minus 7 meters. Thank you, Will. Good? Tom, do you remember what the issue was for that question? Okay. Okay. There's a whole lot of things that could have been the issue with that question, right? Okay. Okay. Let's take a look at number 3 then now. 3 says the diffraction grating is 1,000 lines per centimeter. That's 1 over D, right? We got 1 over D. We'll get D, and we got to get that by flipping it over. We'll deal with that in just a second here. Lambda, 750 nanometers, or 750 times 10 to the minus 9 meters. What's the separation distance between bright antinodes on a screen 3 meters away? That's going to be L. We're looking for X, the separation distance between antinodes. It really should put one more word in there. The separation distance between adjacent antinodes. What they mean here is antinodes that are right beside each other. So what's N going to be if these antinodes are right beside each other? I don't care whether it's the second and the third antinode or the 9th and the 10th antinode. What's N going to be? Right. Now, it's not real clear here with the way they have it worded that it's 2 antinodes that are beside each other, but that's what they mean by that. Okay, on an exam, it would be a little bit more clear what they mean there. All right, what are we looking for? X. Lambda is equal to xd over n times L. Here's a tricky one, actually. Okay, and the reason this is tricky is because our rule of thumb is L greater than 10 times X, but we don't know what X is. So we can't figure out if L is greater than 10 times X, right? So what do we do? Well, you got a couple of options here. Okay. You can actually calculate theta, see if it's under 10 degrees. Okay. You can assume the equation is correct, okay, and then do your little test after the fact. Okay, but in the end, I wouldn't lose too much sleep over the cutoff of whether the equation is valid or not. And the reason I wouldn't lose too much sleep over it is twofold. Number one, they're talking about adjacent antinodes. We don't know if it's the central antinode in the first antinode or not. And we can only use the d sine theta equation if we're dealing with a central antinode. The second thing is, look, if we're looking for x, and that's the only equation with x in it, we don't really have any other option, right? So it must be, it's got to be, in this case, a valid equation. Okay? We have no other option, so we're going to have to use it. Valid or not, we're going to have to use it. So I'm not going to worry about the rule of thumb there. Solving for x, lambda times n times L over d equals x. 750 times 10 to the minus 9 times n is 1 times L is 3 over d. D is 1 times 10 to the minus 3, right? 1 over 1,000 centimeters, or it would be 1 times 10 to the minus 5 meters. What do we get for the value of x there? 0.225 meters. Now, if we multiply that by 10, okay, it works out to be 2.25 meters, which means it is less than 10 times L. Okay, so we assumed that equation was valid. We had to because we had no other option. But as it turns out, it is valid because 10 times x is smaller than can't speak here, the value of L. Okay, does that make sense? Honestly, though, at this point, I wouldn't worry about going back and checking because, like I say, you had no other option in this case. You had to use that equation. And we look at it. What does this look like to you? Two pictures. Let's separate them. What's the first picture look like to you? To me, it looks like bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, right? So it looks like the interference pattern produced by green light as opposed to red light. The picture we always draw involves red light, right? But there's no reason it has to be red light. Okay, if you shine green light through the two slits, you get an interference pattern that is bright spot, dark spot, bright spot, dark spot, but the interference pattern is going to have green light, not red light. You can't get red light when you shine green light through the slits. Okay, so this is what we've been talking about. It's just the diagram's a little bit different than what we usually show. What's the second one? What's the second diagram? It kind of looks kind of the same in the sense that we have like light, then no light, and then light, then no light, bright spot, dark spot, bright spot, dark spot, bright spot, dark spot. But it kind of looks like we have a rainbow in between, like where the dark spots, sorry, where the bright spots are kind of like rainbows. What's going on there? When I draw that picture of the screen with the two openings, and I shine, let's say, green light through those two openings, it produces up here a bright spot that is green, a dark spot, another bright spot, dark spot, bright spot, and so on. Central antinode, first order antinode, second, third, first, second, third on the other side, and so on and so on and so on. If I was to shine green light through there, then I would see the exact same pattern, except red light through there, then I would see the exact same pattern, except it would be red. What if I shone white light through there, which consists of all the colors of the rainbow? White light consists of red, orange, yellow, green, blue, indigo, and violet. Let's take a look at something here. Lambda is equal to d sine theta over n. The value of theta, if we rearrange that to solve for theta, is dependent upon lambda. So in other words, different wavelengths will diffract a different amount. So in other words, we're going to end up with this white light, just like we did with dispersion. Remember when dispersion produced a rainbow when white light went through the prism because there's a different index of refraction for every different color? Different colors refract different amounts. Different colors diffract different amounts as well. So what are we going to get up here on the screen? Well, we're going to get bright spot, dark spot, bright spot, dark spot, except the bright spots will be rainbows. The bright spots will be the colors of white light separated because each different color spreads out a little bit or diffracts a different amount, just like they refract a different amount. So what are we going to see in the middle? We're going to see a central maximum still. That central maximum is going to be, can't really draw this, but it's white light. The central maximum is going to be white. It's going to be all the colors because they're essentially going straight through, right? There's nothing splitting up there. But when I go to the right and see my first order maximum will consist of Roy G. Biv. Well, not really Roy G. Biv. It's the opposite. This would still be my central maximum. This would still be my first order maximum. All of those colors would be my first order maximum. Then my second order maximum would also be this. My third order maximum, and so on and so on and so on. The other side, same deal. First order maximum, second order maximum, and then of course we have all the colors of the rainbow within our first order maximum and our second order maximum here. So how do we deal with that? If we're solving an equation, say lambda is equal to d sine theta over n, what lambda do we use? What theta do we use? Here's what you got to do if you see a question like this that involves multiple colors. It's easy. When it comes down to it, it's easy. Pick a color. Pick a color. Analyze green, or analyze red, or analyze blue. Don't say, oh, look, okay, here's blue and here's red, n is equal to 2 between this one and this one. No, it's not. No, n isn't equal to 2, the distance or the number between the first and the third one for that particular maximum. Okay? If you're looking at green here, the distance from green to green, okay, that would be x, n would be equal to 1 in that case. If you're looking at the distance from blue to blue, that would be x, n would be 1 in that case. You're picking a color. Okay, so in other words, when you pick blue, pretend the green and the red isn't even there. It's gone. It doesn't exist. The green and the red are dead to you. Pretend they're not even there. It doesn't have to be any harder. Okay? You will get a question on your test on Monday that involves white light, like this. Okay? Don't get thrown off by it. If it involves white light, pick a color. If you have data for green light, then ignore all the other colors. Go with green light, even if all the other colors are there. Okay, if you have data about yellow light, then ignore everything else. Even if all the other colors are there, just go with yellow light. That makes sense? This question becomes exactly the same as the questions we've done. Okay, once we recognize that we can ignore all the other colors that we don't have data for. Now, the last little thing that I wanted to say, the last little thing that we can encounter with this thing that makes life a little bit different for us than what we've seen to this point, is that normally what we have here is 2 openings and then a screen up here with a light source. Maybe it's our light bulb. down here. That's our light bulb. It might not look much like a light bulb, but I challenge you to draw a better one. Okay, our light bulb is down here. Okay, the light goes through these two openings, produces an interference pattern. This is white light, actually. It's a light bulb, right? So it actually produced the interference pattern that I just showed you. But okay, that's not what I'm trying to show you right now. Normally, this is what it looks like. But it is possible to have a diffraction grating or a couple of slits that aren't actually openings. Rather, it's some kind of mirror with slits or not openings per se, but little depressions in them that are kind of carved into them or etched into them. And if you have the light up here, then the light can reflect off of those etchings. Now, if it reflects off of those etchings, it's the same thing as if we had the light down here going through two holes. Does that make sense? So if the light goes through those two holes, produces an interference pattern up here, okay, it's exactly the question we've been doing for the last 2 days. If it's not two holes, but rather it's just some piece of glass or some piece of mirror, whatever, and the light is up here and it reflects off of those two etchings on it, then we're still going to get the same interference pattern produced up here on this screen. So if you see a problem where it involves reflection as opposed to actually going through the openings, don't let that mess you up either. Question doesn't change. Okay? D is still the distance between those etchings. Okay, L is still this distance right here. Okay, X is still this distance right here. Okay, theta is still, and so on and so on and so on. Everything's the same. It's just a matter of where the light is and whether it's going through the two openings or whether it's reflecting off of the two etchings or the multiple etchings. All right?